tell me the truth.
I'll tell you the truth, but never goodbye.
Civic is coming! Civic is coming! Why are all these labeled tax credits? Who batched these messages?
They're coming in faster than I can respond.
No more chaos. Just clarity. What just happened?
Was that Civic?
Wow, great stuff. Great stuff, Julian. I'm fired up about that for sure. We've by the way, Julian, you're muted. We've had a lot of hits on that just from LinkedIn alone today. Some people reaching out, few new investors who we've never talked to who are like, yo, saw this video, interested in talking. So yeah, it's been pretty clutch.
Yeah, cool stuff. Yeah, John, do you mind just giving a quick overview of Civic and what we're doing here?
Yeah, yeah. So we started with a correspondence tool. That was the initial pain point that we were solving, and then over the course of the last few months, gotten a lot of new input from chiefs of staff and comms directors and schedulers, and we're now injecting automation into all parts of the Capitol Hill and hopefully state legislature, cities, counties, city councils, all these different government offices to be able to manage their sort of workflow from end to end and up and down the entire team. So yeah, and I think we're going to learn more from Jordan today about how transformers work and how they contribute to the varying AI applications across the Civic stack. So, well, Julian, I'll turn it back over to you.
Yeah, yeah, Jordan, we're all very excited for our presentation. Are you ready to share?
Yeah, I'm super excited. I start with a brief intro of myself. I'm Jordan Mongardini. I've been working as an intern for Civic for the past like 8 weeks now. And I was working as an AI and machine learning intern. Um, and yeah, the presentation I'm giving today is about the paper Attention is All You Need. It was super famous paper that introduced the idea of transformers in 2017 from a bunch of Google researchers. Yeah, let's get underway. Let me just share my screen. Sweet. Oh, that's sorry. I want just a normal. Sorry, guys. I'm normally a um Google Slides user, not a PowerPoint user.
All good, Jordan. I think this works.
I just want to go full screen. Um, there we go. There we go.
Nice.
It's working.
Yeah, yeah, looks great.
Cool. Okay. Let's get started. So like I said, I'll be presenting about Attention is All You Need. It's a landmark paper that came out in 2017 from the Google Mind team. Um, Introduced this architecture known as transformers within the machine learning world. And these are still widely used today, this architecture. So it's super important to the understanding of large language models and other applications. Um, okay, cool. So the first thing to get into, and they touch upon this in the paper, is why were transformers developed initially? And the answer to that question is before transformers, the latest and greatest in terms of technology were recurrent neural networks. So I'm not the um, most educated yet on how neural networks work specifically, but the idea with a recurrent neural network is that you have some input layer and um, it's a graph, right? So there are nodes and connections between those nodes. You start with the connections being randomized, and then through a training process, you end up with specific weights between the node connections, so that when you get to the output layer, all the way here at the end, um, you have the output that you want. Um, so, for example, with text prediction, right? Like you would want to put in a representation of text at the beginning, and your output would want to be that word that you're trying to predict. And these training of these connections allows you to do that. The thing that's special about a recurrent neural network is that it has these hidden layers, and specifically that you have a certain hidden layer that gets fed back. Um, So the idea with this was essentially that by feeding back one of the hidden layers, you get context about other words that you're processing. So for example, um, as you're processing across a sequence of words, a sentence, um, you are able to understand the context of the entire sentence. But there were several problems with this idea. The first is that the entire process is sequential, right? Everything has to happen in order because you process one word or one token, um, and then you feed back the hidden layer, you input another word, and this process continues. Um, so yeah, this is this idea of not having any parallelization. Um, and Transformers attempted to fix that. The other thing was they struggle to process longer sequences and maintain that context the entire time. So, for example, if you're trying to process a long paragraph or even a long essay, um, the neural network would forget about the original context at like the beginning of that essay. Um, And that's this idea behind long range context loss. So, what did the Google Mind team do to fix this? They wanted to develop something that understood the relationships between all these words at once. And that's where transformers come in. So, what actually are transformers? Um, this is an overview of the architecture that they developed. Um, they decided that the best idea was actually to discard recurrence entirely. So we're no longer feeding back this hidden state, as previously discussed, and instead we're introducing this idea called attention. And I'm going to go into the nitty-gritty of attention coming up. But to actually look at the architecture a little bit, what it starts by doing, and I think it's best to explain this in context. In the paper, the original task they were trying to solve was language translation, right? So being able to translate from English to French, for example, or from German to English. And yeah, based off of that, this is where these two sides come in. The left side of the transformer is known as the encoder, and the right side is known as the decoder, right? So this left side in the task of translation would be used to encode the English text, the English plain text, into a deep semantical understanding of the sentence. And then the right side would be used to decode that semantical understanding into the German text or the French text or whatever you're trying to translate into. Another quick interlude. Now, today, this encoder architecture is used a lot for predictive models. So, for example, if you are trying to complete words in a sentence, and I'll show an example of that later. There's models such as this model called BERT, which is widely used. And then on the right side, this decoder stack is actually what has turned into modern language models, or what modern language models use. Yeah. So, with all that context, to actually get into a little bit of the architecture, the first step is you have some input. So this could be any sequence, like a sentence. And this sentence is then tokenized using a trained tokenizer model. And what that means is essentially you take each word and there's a specific do I have a here? This is a great example for it. I'll come back to the previous slide. This is an example of tokens, of a tokenized representation of a sentence. The entire sentence is the animal didn't cross the street because it was too tired. But there are set sizes of vocabularies that these models use. And through that, it's able to split words into these smaller pieces, these tokens. So for example, it split didn't into did, an apostrophe, and then T. So that's kind of a simple concept. Then these tokens are put through an embedding model. And what that does is essentially to convert words. This is a classic NLP or neural language processing or natural language processing task of taking these tokens and vectorizing them, essentially creating a numerical representation of each word through a vector. And we can go more into those specific steps if we have questions at the end. But I think the most important thing to talk about is the actual encoder and decoder stuff, which uses multi-head attention. So I'll describe what attention is and then what multi-head attention is. There's a process of adding and normalizing. Then the resulting vector from this step is put through a feed-forward neural network. And then added and normalized again. And then again, we have this similar process with multi-head attention and a feed-forward neural network. Final little bit before I continue onto attention. The original paper used 6 layers of these transformers in each encoder and decoder stack. So each layer would be one multi-head attention layer and a feed-forward layer, and then continuing with stacks of that. So then to discuss attention specifically, this is the whole idea behind this paper. Attention, the idea is essentially to take each token and understand the context behind that token. For example, in this sentence that we already talked about, the animal didn't cross the street because it was too tired. For a human, it's very easy to understand what does the word it actually refer to, right? The word it is referring to the animal. But this is more difficult for a computer to just inherently understand. So using this attention mechanism, a single pass will generate these different weights of connection, right? So when we're looking at the token it, we can see the darkest color here is pointing towards the animal, the set of tokens. So that's all it does. It processes each token one by one, and correlates it to the rest of the sentence to understand that context. Yeah. So to go more in depth into self-attention, self-attention is when you're comparing the sequence against itself, the sequence to the same sequence. Normal, like attention in general, can be between any 2 sequences. But for our purpose, for this translation purpose, we are trying to understand semantic context against itself with self-attention. Okay. So, like I said, the model allows for association between different words to understand context. And this is the actual process. So, like I said, we have our embedding, which is a vector representation of a token. And there are lots of different embedding models out there. But yeah, all you have to think, long numerical vector representation of a word. And this query vector is representative of this embedding. And then separately, what we do is we use a neural network to train these specific key and value vectors. So if we remember back to my idea at the beginning, we would want a certain model that we train to be able to output these vectors such that we calculate self-attention properly. So that's a very iterative process. But anyway, these key and value vectors are like widely available on pre-trained models. And yeah, so we have our query vector, our key vector, and our value vector. We find the dot product of the query vector and the key vector. And this gives us a score of 112. What we do is then we divide by the square root of the dimension of the key vector. So, in this example, the dimension of the key vector is 64. Square root of that is 8. So we divide 112 by 8. And that's essentially to it's this process that the Google Mind team found created more stable self-attention. Um, then we do this again for the next token. So this is thinking versus itself, but now we're taking um, machines, the query vector, or sorry, the key vector for machines, that token, and again doing the dot product against the query vector for thinking, finding that score, dividing by 8. And then once all of this is done for your size of sequence, so this could also be, like our sentence before, the one about the animal, right? We could go through 5, 6 different words or more. And then you do this softmax operation. All a softmax is making sure that these values add up to 1, but are still weighted. Finally, we do softmax times the value vector, and you result in this sum vector. So essentially, it's just a bunch of linear algebra using trained key and value vectors that allow you to create a numerical weighting, which will show a strong connection between it and animal. So that's self-attention. In terms of multi-head attention, let's move on to that. The Google Mind team, in this paper, they also discuss that they found it was actually even better to have multiple different modules calculating attention, where each module is a specialist in a certain part of sentence structure to get better final results heading into that feed-forward neural network. So, for example, you could have an attention head that is a specialist in punctuation. Like what is the punctuation, the periods and the commas, like what is that contextually related to? Or you could have attention head for verbs, for nouns. You get the idea. So, this is where this idea of parallelization comes in as well. So apart from being able to have a long chain of attention heads, where each attention head is processing one token versus the rest of the sequence, right? So we're already parallelized in that sense. Parallelized, I guess. We also run within each attention head these separate experts in each part of language. So yeah, like I said, these representation subspaces, subject, verb, pronoun reference, and all of this can happen at the same time. So the difference here is that we can actually do this. Self-attention normally is actually calculated with matrices. This matrix multiplication, we're still doing the same thing where we're taking the dot product, but we're doing it in matrix representation, which just offers a nice speed up in terms of the calculation. So again, we embed our input sentence. This top vector here in the matrix is this token. This bottom vector is the second token. And Yeah, we have all of our different attention heads here as rows that are these different experts. So yeah, we have our two embeddings, our X matrix and our R matrix. We split into the 8 different heads, and we multiply this matrix against, again, our weight, or sorry, we multiply against, or we have our query vector that we multiply against the key vector in the same way, the same exact process on each level. And we have this resulting sorry, let me step back a second. We take the embedding of each word, we multiply it against these different weight matrices, we get out our query key and value matrices, then using the same process of finding the score, dividing softmax times value, we get these final Z matrices. And then we take all of these Z matrices and we have this special W matrix, which was also calculated in the neural network step to produce this final Z sum vector. So once we have all of this, this attention step, right, the transformer now has some numerical representation of the context of all the tokens in the sequence. And we've done that in a parallel process rather than having this slow recurrent neural network that has to do this process sequentially. If the more attention heads you add as well, the longer of a sequence you can process. So newer models, for example, will have even more attention heads. But the next step is, as shown in the architecture, to take this resulting vector from the attention step and put it through this feed-forward neural network. So this is a very simple neural network that just goes straight through. It's fully connected between the inputs and the hidden layers and the outputs. And the idea here is, again, to kind of restructure the resulting vector to add more context for the computer. So it uses this idea of nonlinearity, and through training, we get out this further representation of the word relative to the rest of the sentence. And there's going to be some code examples that make this a little easier to understand. Wrapping your head around neural networks just is quite difficult. But it comes out of this process, and we have this final resulting vector that can be passed on to the encoder, where instead it has this full semantic representation of our sequence, and it's able to do this process again to take that representation and turn it into separate, the next language, right? From English to German, English to French, whatever. The other part that we need to touch on as well is that, yes, we've calculated this idea of attention, so we know context as discussed, but we also have to have some way to order, or for our model to understand what order the words present themselves in within the sequence. So because all words are processed as once in this parallel process, the man bites the dog looks exactly the same as the model to the model as the dog bites the man. So yeah, the Google researchers also came up with this idea of adding in a positional encoding vector. So this is just essentially some vector that's calculated through sine and cosine functions with different frequencies that creates this unique deterministic pattern, right? This is a great visual representation of this pattern. You can see that each vector going across that we calculate is completely unique. So for an embedding size of 512 and for 20 words, like we assign the first token 0, this vector, and we continue on. So this would be the word the. This next row would be man. And it gives this mathematical model where the transformer can understand the order that the words in the sequence or the tokens in the sequence present themselves. Just easy to calculate. And I'll show you as well here. This is where this comes in. So let's really quickly do this recap. We have our tokens that have been embedded into vectors. We add these positional encodings as previously discussed, which again are just another vector of the same size. Thinking machines is put through the self-attention step. The positional encoding is added just straight on top, like the zeroth indices are added together, first indices are added together, and then they're normalized back to be within that soft max of all adding up to 1. They're put through the feed-forward neural network, which now has context and position, and then they are added and normalized again. And we continue onto the second encoder, as you can see here. So that's the entire idea with transformers. The big question is, why do we care? So this actually comes from the paper, this table. This was a table that showed the specific thing called a BLEU score, that I'm not super familiar with, but essentially it's a numerical representation of how good a person or a model is at translating language. So, previous models. Well, if we look here, this is this BLEU score that I just talked about. This is translation from English to German and then English to French. And these were previous models that used recurrent neural networks or maybe some previous technologies as well. And they have, this lower score of about 40 and around 25. Some more models here. And then this is where transformers were introduced. They had a base model, which was, I believe, just 6 stacks, encoder-decoder stacks. And then they also created a much bigger model that took 3 days to train rather than 8 hours to train. And we're already achieving higher scores with this transformer model. But that's not the big exciting bit. The big exciting bit is this training cost. So flops is a representation of computing power. So with these bigger models, it took you know, multiple factors more of computing power or flops to train each of these models. And rather with a transformer, we're only at 10 to the 18th rather than 10 to the 21st or 10 to the 20th. So we could train even bigger models than ever before, really quickly and with not that much power. So they set brand new records on all these different NLP tasks. And then, as I said in the beginning, even today, exact same architecture. Well, people have made tweaks to see some improvements, even further improvements, but the same overarching architecture. Encoder stacks like BERT use that left side, like we said, that were and they're able to understand the super deep context understanding. And then models like GPT, Chat GPT, are based off of the decoder stack, making them really good at generative tasks. So, a lot of words. Let's look at a bit of a code demo. So I think even more examples make it make even more sense. So this is just a Jupyter notebook. For this, we're going to do four things. We're going to look at the input embeddings, the multi-head attention, feed-forward neural network, and then what the whole process looks like together. So for this, we're just using this standard pre-trained BERT model. So just a stack of encoders. We have a tokenizer. And yeah. So this is a printout of the model itself. Here we can see there is embedding size. So for this, we can see what size of embedding vectors we're creating. These are the positional embeddings that we talked about. You can see, where is it? We're doing 12 BERT layers. Each of those layers is one full transformer. And then we have other things like, for example, I think somewhere it says how many attention heads there are. BERT self-attention. Yeah. 768 attention heads, I believe. But anyway, to look at the embeddings, what we do, again, we tokenize. We break down each sequence of words into these smaller words or parts of words. And then each of those tokens has an ID. So we can see this here. And once we have that token ID, we convert into vectors through the embedding model. So our sentence is the animal didn't cross the street because it was too tired. Same sentence from before. We convert into these tokens. The animal didn't blah, blah, blah. Then we have our giant, a huge vector of the token library or token vocabulary. And for example, B is translated into token ID 1996. So at position 1996 or indice 1996 in the vocabulary, that is where this token occurs. So we have this big tensor of each of the tokens, and then we embed each one. So essentially, we're creating a 768 length vector, 768 dimensions. And then within each of these tiny little slivers is some value between, I don't know, like -12 and like -4, each of these little slivers. So you can see how it becomes this vector. Then the multi-head attention. So here we are taking each of these vectors and passing them through each of the parallel attention heads. So out of this is all self-attention again, so it's being compared against the same sequence. And here we have 12 different attention heads. And this is the same idea as before, except, here we can see, before we were just seeing the word it against all of the other tokens in the sequence, but now we're seeing all of the tokens against all of the tokens in each of the heads. And here it's super easy to see that each head has its own specialty, right? Otherwise, these would all be the same values. But yeah, we pass through each of these heads, we get out this context representation, and then they're passed through this feed-forward neural network. For this feed-forward neural network, this is the initial embedding. So that first graphic we saw of the word animal, the token animal. So this is the initial embedding, and then this is the final encoding. So this is after it's been through all the attention steps and also through the feed-forward neural network. We have this new vector representation that then, for example, in a large language model, there's something known as an LLM head, which is able to then take this final vector and interpret it to produce the next or generate the next token. And we'll see this here by putting it all together. What I did here is essentially I took the entire sentence. The animal didn't cross the street because it was too tired, or the road. I masked one of the tokens. So this is a sentence completion task, which is what a model like BERT, an encoder stack, is really good at. And then we just run the whole process together through the encoder stacks, and you can see these are the top 5 predictions, each of the tokens. Its top prediction was road as a score for each of like what it thinks this missing token is. Yeah, so that was the code demo. And now I'd be extremely happy to take questions, discussion. It was a lot of information. But yeah. You can just start talking if you have any questions.
Do you feel like you got any more insights into how to use AI models now that you understand the fundamentals a little bit more clearly?
Yeah, I do. I think this overarching idea of like having these different NLP tasks, right? And that an encoder versus a decoder is better for different tasks. And that also, by understanding the architecture, you can dive into each step and potentially train the matrices or the feed-forward neural network or whatever better to suit your task. So I think understanding that architecture is huge. I think for me, the next step is to really understand how to train neural networks as well. But yeah, I was like very happy to finally figure this stuff out. Any other questions?
let's hear some questions, unless everyone thinks they understand it perfectly.
I just want to say great presentation, Jordan. And like when you spoke about the attention dropout that randomly turns off some attention links during, say, training, so that like the model doesn't get stuck on some irrelevant parts, like that now makes a bit more sense when like I've seen this help uh, the model classify the emails more accurately for tricky buckets like grant information versus appropriation during my bucketing task. So that gave a bit more clarity. Thanks for that.
Yeah, of course. Happy to hear that. Thank you.
It's still a little what's the word? Unintuitive to me that recurrent neural networks turned out not to kind of be a promising path.
Yeah.
Is when I read a book, I don't stare at all the pages at once and then absorb, the full book that way. I, read a couple words at a time and, over time build up the full understanding of the book.
Yeah.
Uh,
But for example, Julian, imagine a giant prompt passed into an LLM, right? We want to be able to understand at all times the context of that entire prompt. For example, if we're instructing an LLM not to, um, I don't know, to pull information from like this specific location, but then way later on we're asking the specific query. Um, that might delve a little bit more into memory within LLMs, but yeah, I think that's part of it, that we're actually able to have this bigger context window. And then the other thing as well is just this much faster training speed or less computational power to train an equivalent model size.
yeah.
I was gonna
Yeah,
ask.
that's really accurate from my from the ways that it talks about it in classes I took is that it's like it's actually mostly about the parallelization. So, RNNs, you need to actually go through every single step and train all of them. Um, but also like they were state of the art for years, right? It's not like they were, that's why they bring them up is because like people thought, well, this is like really the only way to do it. Um, it's just the tension is like so, so much better that it looks like out of date now.
From what I remember though, after like I forget the exact number, but let's say like 15, 17, I think it might have been even like seven, recurrent net passes, then the model performance starts degrading. Um, so I wonder if that was just a data problem, or a number of model weight, problem, or whether that's kind of like a permanent problem and maybe like recurrent neural nets will come back to um, be some, partially relevant in some way. But
I think that is like because those like RNs like rely on single hidden state at each step, like so that is why it maybe finds it hard to uh, you know the relationships that are distant are harder for it to understand compared to like say transformer self attention,
yeah,
which like as Jordan mentioned, it looks at all the words at once, right?
Yeah.
I,
I might have to dig into a little bit more of the details there. I think I mean I think for them, right, the biggest idea is like once they saw this parallelization and how much that decreased the flops required to train their models, that was a significant enough technology leap. Um, for all these different AI labs to just start going down that path.
Something
That's like my idea.
a long time ago was, or a good explanation for why transformers became were so powerful is that like are you familiar with convolutional neural nets? So what convolutions achieved is that instead of when we had very limited amounts of data, telling the AI to just kind of like focus on a limited space, what are just like the nearest nine or whatever it is higher than that, 15 um cells, and looking at that to form larger, shapes and features,
Hmm.
uh, allows the AI to much more efficiently use the amount of training data it has. But as we've gotten more and more and more training data, we were able to kind of let go of that restriction and tell the AI instead, hey, look at, everything at once. Um, and it's that kind of like increase of training data plus the number of model weights, which I guess here was like a really big breakthrough. But
Yeah, I think that intuitively makes sense as well.
Maximus has a question.
Yeah. Um, so I think it depends on the task as well. Maximus's question for anybody not reading the chat is how do we make sure a transformer only tells the truth and keeps accuracy? Um, so for example, in our um, sentence completion task, we saw that there was a like ranking with different scores for each complete word. And you can then take those scores and interpret them um, kind of as you will. But I think the bigger idea is with like LLMs, right? Preventing hallucinations. And that I don't think actually comes down to the transformers itself. But actually, when you have a huge, when you have an LLM, the actual prompt engineering, um, and also doing like sanity checks. I think that's the biggest way that we can minimize hallucination. Um, but I also want to delve into that more because I want to try and understand like how these hallucinations actually arise. Um, like in the very deep technical details. Um, but I don't know. Does that kind of answer your question? So it's part of when you're writing code to lever. Sorry, I'll repeat the question. Um, Maximus's follow-up question is,
I
so the
hear.
sanity check, are they like automated or does a human review the output that it sends? Um, in most of the tasks that I've seen, or most of what I've used LLMs for, it's the human doing some sort of sanity check in fine tuning of the LLM. So that's code that you write yourself. So yeah, kind of the human doing the process.
Okay, thank you so much. That's very cool. This is helps me understand what we're doing more, honestly. Hopefully I can apply that knowledge. Apologize for not reading the question out loud.
No, you're totally fine. More than happy to read it. Okay. Any final questions? Going once, going twice. Okay, cool. So final thing I wanted to say, well, thank you, of course, for the opportunity to give this presentation. Hope it helped somebody, um, you guys learn some more about this. But the big thing I wanted to say as well is that a lot of the visualizations, these like graphics with the vectors being multiplied and stuff like that. They're pulled from this illustrated transformer guide, or this illustrated transformer paper. So I'm actually, let's see if I can throw this into the chat. It's a paper that I used, which really helped me to understand the entire, or the illustrations and the way they explain it in this paper really help to understand the actual paper. Attention is all you need. Um, and yeah, I just wanted to give them a big thank you. That helped a lot. So yeah, I'd recommend that resource if people want to learn more. And then at the end of that paper, there's even more resources like a uh, um, what is it? Deeplearning.ai course, which I also took, which was useful to understand this. So yeah, thank you. Let me try and get that link into the chat. Okay, cool. Link is there.
Amazing. Thank you so much, Jordan.
Yeah, of course. It was a pleasure.
Thank you so much.
Cool. Cool. We'll just end it there. Hope everyone has a really amazing rest of their week. And Jordan, hope you have an amazing time in Sweden.
Yeah, thank you. I'm super excited. All right. Thank you guys. Have a good rest of your week.